Hello, my name is Harry, and I will be presenting my Lab 3 on magnetic field of a bar magnet. The purpose of this lab was to determine the dependence of the magnetic field due to a small bar magnet with changing distances. To give an overview of this presentation, I will be going through the introduction, experimental results, computational model, and then a discussion. The fundamental principles that were used in this lab were the Biot-Savart law, which calculates a magnetic field for a given radius, and then the dependence of magnetic fields as listed in those two equations below, and then finally magnetic dipoles and the interactions those have with other objects. Some observations from this lab were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. The position of the magnetometer has no effect on the measured x component of the magnetic field. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The first part of the procedure was locating the magnetometer. First, slide the phone perpendicular to the ruler until Bx is at a max and By is at a minimum. Then, mark the tape and rotate 90 degrees. Repeat this process again with a new orientation. Then, the intersection of tape is the location of the sensor. Part 2 of the procedure was measuring the magnetic field. 0 Bx component, then find the distance d horizontally where the magnitude of B net equals 100. Record By, then move the phone distance d vertically. Record all components of magnetic field and repeat this process 2 times. Now onto some experimental data. On the left side of the data is the on-axis results that shows the distance where the magnetic field is equal to the numbers on the left. And at the bottom is the off-axis field, and by 3 trials to give both the distance and net magnetic field. At the bottom again you can see that there's a By corrected, and this is to account for the Earth's magnetic field, which is done by subtracting the measured value from the Earth's value, and then the graph shown is a linear plot of dx and r. This is done by taking the natural log. And then we can represent this by using the distance dependence formula, one of the equations, to form ln bx equals n ln r plus ln k, where k is a constant, and n is negative 3.1494 meters, which should be about 3, as that is the distance dependence r cubed of magnetic dipoles. Here are some calculations where the distance dependence of magnetic fields formulas were used. Those were mentioned earlier in the presentation, and from those mu was calculated, as well as r, which is 1, as you can see down below. The results from all of this was that d was equal to 0.255 meters, n was equal to negative 3.51 meters, mu was equal to 2.136, and the average magnetic field off-axis was the vector, the 3-dimensional vector listed there. Here's the computational model, which takes the results and visualizes them. And this visual here, and as you can see, d was 1.41421, and the b at 45 degrees at distance d was that vector there. Here are the compared results. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? In the x component, because orienting the experiment to compensate for magnetic more north meant zeroing out the x component of the magnetic field, and if I didn't do that, my x values would have changed. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The measurements would have increased.